Rotational kinetic energy, problems with conservation of mechanical energy. So the best way to teach this concept or problem type is to begin solving a problem immediately. A 20-kilogram solid disc or pulley is attached to a hanging 10-kilogram block, which is released from rest 500 meters above the ground. How fast will the block be moving just before it hits the ground? So there are many ways to solve this problem, but today we are going to solve this using conservation of mechanical energy. And what we are going to do is we are going to investigate each important object in this system, and we're going to figure out what their energies are and what happens to their energies after some time. So the first thing that we need to do is to figure out what are the important objects in our system. And I have written here that our system should consist of the pulley, or the solid disk, the box, and the earth. So I included the pulley because it says in the problem that the pulley is actually attached to the block, and I imagine that as the block goes down, that the pulley will also rotate. So I imagine that the pulley will have some sort of rotational kinetic energy. And so I'm going to write that down, that the pulley has a kinetic energy rotation of, actually, let me introduce you to another way of writing kinetic energy rotation, which is just to write letter K. And then the formula, of course, is 1 half I omega squared, which I hope you still remember from our previous video. And also, I included the box because the box has a certain height, okay? And that height changed over time. So I'm pretty sure that the box has a potential energy and a kinetic energy. Okay, but I'm gonna just write, perhaps this box has gravitational potential energy of mgh. So you're probably wondering, why is this U? This is just another way of writing potential energy. Maybe you're used to PE, but this is I think I like this better, U for potential energy. And I included the Earth because the Earth, oh, wait a minute, I'm just gonna add the kinetic energy of the box because I mentioned that it is moving, right? It has to be 1 half mv squared. And I included the Earth because the Earth is what's providing the gravity, causing the object to fall down. Now, you're probably wondering, doesn't this pulley have potential energy as well? It does, but this pulley is fixed. So I don't think it won't have any significant contribution to this problem because it doesn't change anyway. So we're dealing with changes in energy, and that's what helps us solve problems. So the pulley will have a change in rotational kinetic energy, obviously, because it starts off, because the box is released from rest, it starts off with zero angular velocity, but eventually it will rotate, and so it will have a change in kinetic, rotational kinetic energy. The box also will have a change in energy, so that's why I included the gravitational energy of the box. Now, the mechanical energy is the sum of all kinetic and potential energies in a system. And the conservation of mechanical energy states that mechanical energy is conserved in time as long as the only forces acting are conservative forces. In this case, we are assuming that there is no friction between the rope and the pulley, because if there is friction, then we cannot use conservation of mechanical energy, because friction is not a conservative force. It is a non-conservative force or a dissipative force because it takes away some energy from the system and converts it into heat. But Aside from that, the only force acting in the system is gravity, and gravity is a conservative force. Gravity doesn't take anything away, and it doesn't convert anything to heat. Gravity is a conservative force. Let's use an energy bar chart or a LOL diagram to visualize energy transformations in the system. Not sure if you've heard of a LOL diagram or an energy bar chart, but I'm gonna introduce you to the LOL diagram. It's called the LOL diagram for obvious reasons. And I'm gonna focus on this O or circle in the middle. This is where you draw your, you write down your objects in the system. So I'm gonna write down pulley, just so we have a wonderful place for all our object systems to be in. The box is also there, and the earth. And what are these L's? These are actually bar charts. And the first L is for the initial time, and the second L is for the final time. We're considering changes in time from one time to the next. And we're using conservation of mechanical energy to show that the total energies at one time is equal to the total energies at a later time. So here in this first L, we write down all the possible energies that we have. K trans is one, or the linear kinetic energy. And we have UG, and we have K rot. These are all the possible rotational energies for the initial time. And for the final time, we also have all the possible energies, K trans, UG, and K rot. And the rules for drawing a LOL diagram is you have four boxes, one, two, three, four. And actually you can divide each box into these little triangles. And you try to estimate how much of these four boxes, how are they distributed among these three energies? Are all four boxes set up in just one energy, or some of them is in UG while the others are in K trans and a few are in K rot? And that's just one way to visualize. You don't have to be too accurate, but by doing this, you visualize what happens to the energies, where they are, and what happens to them in the future. So let's start here in the first initial L. Initially, the box is at rest, which also means that um, this pulley is at rest. So they don't have velocities. Initially, there is no angular velocity for the pulley and no linear velocity for the box. So what happens is, I'm going to put an X here for K trans because nothing happened. There was no translational kinetic energy. And I'm going to put an X here for K rot because the pulley isn't moving. That means all of my four boxes are stacked up under UG. And it makes sense because the box does have some height. So it does have some gravitational potential energy. Now let's look at what happens after. And after means this second sentence, how fast will the block be moving just before it hits the ground? We're referring to just before it hits the ground where we're looking at after. So this after L, or this later time L, is referring to when the box is just almost about to hit the ground. That means it still has translational kinetic energy. It no longer has gravitational potential energy because it's in the ground, basically in the ground, almost there, and just a small infinitesimal distance between the bottom of the box and the ground. So basically, wala na siya gravitational potential energy. But it does have rotational kinetic energy because the pulley is rotating. So I think we can have I have a feeling that I should distribute the four boxes, two and two. But it doesn't really matter. It doesn't matter at all. What this does though, it allows us to set up an equation. UGI equals K trans F plus K rot F, where F stands for final. And we're actually looking for VF. So that's what we're looking for. Okay. MGHI. There's one more important step. And here we are referring to the mass of the block, right? Because this is the gravitational potential energy of the block. And the height of the block. Height initial of the block. And here, K trans, we are of course also referring to the block because the pulley is not moving translationally. Mass of the block and velocity of the block squared. And this is what we're looking for. And K rot F is 1/2 moment of inertia. This is for the pulley, moment of inertia of the pulley, and angular velocity of the pulley final squared. Now, seems difficult because we don't know what omega is. But here's very, very important idea that the velocity of the block is equal to the rate r omega, r of the pulley and omega of the pulley. So the velocity of the block, the linear velocity of the block is equal to the omega of the pulley and r of the pulley. And where did this come from? This comes from the fact that the final the velocity of the block is just equal to the tangential velocity of the pulley. And why would that be? I leave you to think about it. Why would I say that? Let me draw it here. This tangential velocity of the pulley is equal to the linear velocity of the block. I'm not going to explain why that is, but I think you have an idea why that is. Anyway, so we can now make some substitutions. But also before that, I want to point out that the moment of inertia of the pulley, which is a solid disk, is 1/2 mr squared, where r is the radius of the pulley. So let's make some substitutions. We copy that, we copy that. I'm not gonna substitute 1/2 I is a 1/2 mr squared. And we mentioned that omega is the V block is omega P over RP. So we um, transpose R, we'll get the velocity of the block over radius of the pulley is the radius of the pulley squared. So you can see this RP will cancel out. So that's why wala given an RP here because it will cancel out anyway. So what happens is MBGHIB is equal to, right, I should have just typed this earlier, plus the 1/4 mass of the pulley, that's the mass of the pulley, right? And the velocity of the block squared. All right. So I'm really having a hard time writing using this PowerPoint pen, but since everything is given here already, I want you to check that you will get 70 meters per second for the velocity of the block, right? Right. So you know that our mass of the block is 10, g is 9.8, height initial of the block is 500, velocity of the block is this what we're looking for, mass of the pulley is 20. So we have everything at our disposal. We know the values of these variables, and we can now solve for VB by algebraic transposition. Oh, that's all, I guess. And I want you also to try to solve this. This is for sir sinus lang, no? Right? And maybe we'll do that next meeting, but you can do this now. And how about this? Okay, thank you.